While this section is really the beginning of applications of trig functions to real-world problems, let's first look at an important relationship that we've already seen so far. Suppose we're given the following right triangle with sides B, A, and R. This is 90 degrees, and the angle over here is theta. Then we saw that sine theta is equal to A divided by R, and cosine theta is equal to B divided by R. We can rewrite both of these rather simply as follows. R of sine theta is equal to A, and R of cosine theta is equal to B. One thing that we've seen so far is that we can embed right triangles into a circle of some radius, like this, and the point AB is a point that lies on that circle. So the relationship that we've just introduced, AB, we can rewrite using trig functions. So this is going to be equal to the radius of some circle times sine theta, comma, the radius of some circle R times cosine theta. This is an example of a coordinate system called polar coordinates. Polar coordinates are useful for spherical surfaces in Calc 3. They come up in physics, and overall, they're a very useful coordinate system. While we won't talk about them much more right now, I thought it would be a very good idea to introduce this coordinate system so that you can see where it comes from. Let's now look at an application. This is the final example in this section. And to estimate the height of a mountain above a level plain, the angle of elevation to the top of the mountain is 32 degrees. Then, 1,000 feet closer to the mountain, along the plain, the angle of elevation is 35 degrees. Estimate the height of the mountain. Here we're given 2 or 3 pieces of information. First, at our initial point, we see that the angle of elevation is 35 degrees to the top of the mountain. So this is 35 degrees. And here's our mountain. Then 1,000 feet closer, somewhere over here, we see that the angle of elevation is 35 degrees. And from this, we should be able to find what the height of the mountain is, approximately. And I made one little mistake. This should be 32 here. So let's go ahead and name some more variables here. We'll call the height of the mountain H, and we'll call the distance from the point that's 1,000 feet closer to the mountain D. And we also don't know what R is over here, but we'll go ahead and label it. In this case, we want to come up with a trig ratio that's going to be most useful for solving this equation here. I think in this case, since we don't know what the hypotenuse is at all, it would be more prudent to use tan theta. So let's go ahead and look at tan of 32. This is going to be equal to the height divided by the adjacent side, which is 1,000, plus the distance. And then the tan of 35 is going to be equal to, again, the height divided by the distance, which is d. So let's take these trig relations and start a new page. Here we see that we could solve this equation for d and plug it into the first equation. Here we see d is going to be h divided by tan of 35 degrees, which means that rewriting the first equation, this is going to be tan of 32 degrees is equal to h divided by 1,000 plus h divided by tan of 35 degrees. Now this is a rational equation, which means we know how to solve this. We can go ahead and solve for h, multiply both sides by the denominator over here, and we'll get tan of 32 degrees times 1,000 plus h divided by tan of 35 degrees is going to be equal to h. Then distributing out the 32 degrees, tan of 32 degrees, we'll get 1,000 times tan of 32 degrees plus h times our tan of 32 degrees divided by tan of 35 degrees is equal to h. Subtracting this term from both sides and then pulling out the h, we'll get 1,000 times tan of 32 degrees is equal to 1 minus tan of 32 degrees divided by tan of 35 degrees. All this multiplied by h. Then what we'll see is that h is equal to tan of 32 degrees times 1,000 divided by 1 minus tan of 32 degrees divided by tan of 35 degrees. Here I've also included just an approximation of the solution if we plugged it into the calculator. So the mountain is approximately 5,806.709 units tall, whatever the units were.